Well, welcome, everyone. Thanks for coming. My name is Ryan. I'm a software engineer at Lyft. I work at the office here in Seattle, so it's great to be at a local conference. I'm surprised by this amount of people. I should maybe start with a disclaimer. You can see the talk title. You know what that is. I ran into a friend as I was coming in. I haven't seen him in a couple of years. He said, "Your talk looks interesting. Does this mean I don't have to use YAML?" And I want to make a disclaimer. Whatever the opposite of that is. So if you need to get up and leave right now, no problem, no judgment. No. So this is encouraging you to embrace the YAML. And we're going to talk about how you can deploy your applications more easily and more customized with this tool. It's an open source tool. The structure of our talk, we'll take a look at the landscape. As with most things Kubernetes, sometimes it's difficult to sort of place this in the overall context of all the other tools out there to understand what problems it solves, what problems it doesn't solve. We'll look at some features briefly, and then we'll dive into a demo. And we'll spend most of this talk doing a demo, actually. That is kind of non-trivial. We'll deploy a piece of software from an upstream. We will start layering in various configuration. We'll push it out to GKE and use a bunch of the cloud features there as well. So that should be good. Hopefully the Wi-Fi holds. So lots and lots of different tools out there today for deploying your applications. You probably have been to talks at this conference on one or more of these other tools. Helm is probably the most popular. Maybe you've seen what the folks over at Pulumi are doing, sort of a different take on things. It's quite interesting as well. There's KSonnet, there are these other tools, and there are many, many more. So when looking at them, sometimes it's useful to develop even just a coarse-grained taxonomy of what these tools offer. Some of them offer dependency management. They tell you if you're going to install package A that you need to install package B and C previously. Some of them provide application descriptors with URLs to upstreams, different metadata associated with the application. There are application discovery systems, things like Chart Museum, where you can go out and actually search for an application. There are dashboards that live in your cluster itself to tell you the current state of applications, their versions. There are tools that let you manage the lifecycle to deploy specific versions, to roll back and control the lifecycle of your applications. And then there are capabilities of these tools that allow it to be customized or adapted or tailored to your specific needs. And in fact, that is the domain of Kustomize. It is a very targeted tool. It does not try to accomplish all of these other things. It's really doing one thing, and that is allowing you to tailor your YAML files to your specific environment. So it's very useful in many developer workflows, and it can find a very natural place in some CD pipelines as well. This is the description from the README file on the Kustomize GitHub page. It lets you customize raw template-free YAML files for multiple purposes, leaving the original YAML untouched and usable as is. So this is really a key idea that we'll come back to, we'll develop, we'll sort of parse this and really understand what that means. A very simple invocation of it is shown below. You'll run the CLI tool from the command line, kustomize build. It looks in the directory at the contents of the files, pulls those in, processes it, and outputs the result to standard out. So a very common flow is simply to run this tool and pipe it, as I'm doing in this case, directly to kubectl apply, and you will immediately have those changes applied to your cluster. A new configuration file is introduced here by the Kustomize tool. So customization.yaml is basically what parameterizes this tool. So you may have some existing YAML descriptors that are ready to be deployed into a Kubernetes cluster. You can drop a customization.yaml file in adjacent to those other files and begin to define new behavior that will be performed during the build process. So in this case, this is pulling in two resources. This is assuming there is a deployment and a service YAML adjacent to this file on the file system. And so when build runs, it will pull these files in, and then it will stamp this kubecon namespace to all the resources in that file, in those files, and emit it to standard out. So that would be a very, very simple use case. You may be thinking back to the 70s here and the Unix philosophy of doing one thing well, and that is very, very much the ethos of Kustomize. It's a very targeted tool to allow you to manipulate YAML, and not just any YAML. This is manipulating specifically Kubernetes API YAML. Kustomize has its roots in this paper written by Brian Grant, Declarative Application Management in Kubernetes. If this is a general area of interest to you, even if this tool is not of interest, I would strongly advocate that you go read this paper. It's quite interesting. It's available on GitHub as well as the Google Doc. You can just Google for it, and you'll find it relatively quickly. But it talks about the motivation, it talks about other tools in this space, and it talks about the general concept of splitting apart some of the functionality of these tools, these monolithic tools, and exposing things like Kustomize to handle these very purpose-built utilities. Let's look at some features. So once again, you see a customization.yaml file and a pod YAML. So a pod YAML should look very, very familiar to everyone in the audience. This is a super simple pod spec that's defined here in a YAML file. This is sort of ready to be applied to a cluster. All it would do would be spin up this BusyBox-based container. I'll point out that that pod is called snooze if you look at metadata name. So customization YAML, if it sits adjacent to it on the file system, you'll notice at the bottom, resources pod.yaml, so it's pulling this into the file system, and then it will stamp onto that these custom labels and these custom annotations. Further, it will apply this prefix of pre-production to each of the resources processed, and it will drop that into the customer preview namespace. So again, you run a customized build with those two files in the file system, and you'll see something that looks much like this. It's very similar to the original YAML. It's been augmented with these annotations, with these labels. You'll see it's reached down into the metadata name, and it's altered that name by prepending this pre-production dash prefix to it. And it's placed it in this namespace. A super common workflow that's enabled by Kustomize is this notion of overlays. So perhaps you've got a team within your company, or you've pulled down something open source, or you're collaborating with someone. They provide you a set of descriptors. It's almost what you need, but you need to customize it. You need to tailor it for each of your various environments in some specific ways. So Kustomize enables this via overlays. And so Base can contain most of your descriptors, and then in each environment, you can specify the different changes you want to apply to it. So let's break this down. What would that look like in practice? I'm showing an example here of 3 directories on a file system. One that's called base, another called production, another called staging. Base contains that similar simple pod specifier along with a base customization YAML. And then in production and staging, that's where each of the changes per environment are applied to it. What connects the two are the bases specifier that you see in the lower pink box where it says bases and is referring back up on the file system to base. And so if you run customized build on this, it will do what you would expect. It pulls in that base, and it applies whatever changes, not just a prefix, but you can apply anything that Kustomize can do to whatever was contained in base. And it has a sort of interesting recursive property that you can take these simple primitives and compose very sophisticated capabilities and behaviors out of it. You might also want to do a mix-in configuration. At Lyft, we have a sophisticated system that uses this mix-in workflow, where basically you've got a bunch of different modules, and there are many different deployment configurations that are supported. And for example, what I'm showing here is you've got a UI module, a backend module, and you might want to deploy this in a headless configuration where you've got no UI, or maybe you want to deploy it in a complete, where you're saying take all my modules and deploy them. And so Kustomize supports this. This is very similar to the other example we looked at. If you'll notice at the bottom, again, this is referencing bases, but you'll notice that you can pull in more than one. So by allowing you to pull in more than one base, you can sort of get this interesting mix-in behavior. And so in this example, I've got this base modules directory that contains all the modules. In the complete configuration, I'm pulling in all of them, and in headless, I'm just pulling in the back end. So you run customized build, it will do what you would expect. It pulls all those things in, merges them together, and outputs it. When working with Kubernetes, especially if early on, you were probably surprised when you made a change to a config map, pushed it out, and nothing happened. Kustomize can help with this as well. So there's the notion of a config map generator built into Kustomize, where it enables you to externalize the contents of your config maps, so they can sit outside of YAML files. They can sit in, for example, files on the file system. So here in this example, in config map generator within customization YAML, I'm saying db params is going to be defined by everything contained in this list of files, in this case, db.toml. So that's one flavor of config map generator. The other is the specification of just literals. So I've got just literal key value pairs where I'm specifying Java Home and Java Tools options. So what would that look like? You run customized build on that. It's going to output something that looks like this, where db.toml is pulled in, and you'll notice that the base name of the file, db.toml, becomes the key in the config map, and the value is the unstructured contents of the file. You'll notice down below that literals are basically converted directly over to their corresponding key value pairs. And then maybe if you've got a sharp eye, you've noticed that the name of the config map was altered. And so the idea here is that there is a suffix appended to the config map name based on the hash of the contents of the config map. So any changes to the config map, it will rotate the name of the config map. And not only will it do that, it will find every other reference that you have to that config map within your specifiers, and it will update those linkages. So the net effect is when you change things within, like for example, db.toml, and you run customize build again, push that to kubectl apply, it will trigger a redeploy for you. We'll look at examples of this. So if you're not totally grokking all this as we go, don't worry. Super common use case is patching. Again, maybe you've been provided a set of descriptors, and you want to sort of reach down into the tree, and you want to add some content or change some content. Kustomize supports the ability to apply patches. So you'll notice on the right-hand side in Kustomize YAML, we have a list of patches. In this case, I've just got one entry called request limits. So that pod, you'll recall, it was very simple. It had no resource specifiers. We were not specifying any request resources or limits. And so what this does is it provides a fragment. This patch provides enough of a fragment to identify where in the target YAML that you want to apply this patch, and then it will, via strategic merge, pull that in. So if you're on Kustomize build, you'll see again the contents of that original pod spec listed, unioned in with those limits and request resources via strategic merge. We'll see more examples of this as well. Let's do a demo. The paper I referred to earlier by Brian Grant talks extensively about this fork modify rebase workflow, this concept where you can locate an upstream, find some interesting YAML descriptors that are located there, fork the repo, and then start dropping in customization YAML, your patches, your config maps, alongside the original descriptors without altering that original file, and then using Kustomize to deploy this out to your environment. And so that's exactly what we're going to do. We are going to use this kind of a GitHub clone called Gitty that is actually surprisingly capable. It's an interesting product. I recommend you take a look at it. But it's good for our purposes because they happen to ship with a default descriptor. That we're going to take that descriptor. I forked this whole repo. So if you go to github.com/Ryan Cox, I've pinned that fork up at the top. And I've created a couple of branches where I've started to apply in various behaviors that we will compose and deploy out to GKE and see how this all works. Ultimately, we want to build up to a kind of a non-toy, non-trivial workload that looks something like this. We want to basically tap into some of the other cloud resources that are provided. Gitty supports a bunch of different backends. Our initial version will deploy with SQLite. A subsequent version will use Cloud SQL and a hosted Redis store. The first thing that we'll do, though, is we will use persistent disks. So the example that's provided by default, it actually wouldn't even work if we tried to apply it because it's using some host paths that don't exist on my nodes. So that's our first goal. Our first goal is to just get this thing working in GKE and get it using persistent disks. Then we'll layer on top of that some more complexity. If we have time, we'll show something a little bit more fancy. A lot of talk about service meshes, a lot of talk about Envoy. At work at Lyft, we sprinkle Envoy on all our problems. So I want to show an example of how you can use Kustomize to inject an Envoy sidecar into an existing pod spec. And this is an interesting use case because maybe some of you are using mutating webhooks to do this sort of thing on pod deploy. This shows kind of a different approach where if you're using GitOps, you could actually sort of like inject it into your YAML, check that in, and deploy it out. So this is maybe like an idea virus I'm hoping to put out there into the universe and see it fully formed by someone else. But the general idea is we'll inject this thing, and we'll access it via 92.11 and see how that works. OK, so let's get into the demo. This demo is a little bit elaborate, so I'm hoping that the demo gods are smiling on me. Let's take a look first at this repo here. So this is the repo for the application that we're going to deploy out to our GKE cluster. And you'll notice down here in contrib-k8s, they've got this YAML file. This is like pretty vanilla. There's nothing too surprising here. They define a namespace. Hopefully you can see that. Zoom in just a little bit more. A deployment. That deployment has a pod spec with a single container in it. Some vol mounts, root and data vol mounts. These will become important to us as we start to adapt to this thing. They expose out a couple of different ports. And here's the first problem is we want to get rid of this. This is bad. This is going to cause us some problems. We don't want host paths. We want to use these persistent disks, okay? So that's what we're going to start with. Let me show you my environment out in Google Cloud. So I've got this KubeCon cluster. Actually, I can just go back here. I've got this KubeCon cluster that is got 3 nodes on it, 3 vCPUs, and a few gigs of memory. So that's what we're going to deploy all this stuff onto. Let's go into the file system here. So I'm out on the file system. I'm in the fork, and I'm on master right now. This looks just like what we looked at while we were browsing, right, through GitHub. Now I'm going to check out demo step 1. OK, so demo step 1 has a few more files in this directory. So again, this concept, I've mentioned this twice, but I just want to reiterate this. The original Git YAML file is untouched. We just leave that there, and we drop in other files alongside it in the file system to compose this behavior and for customize during the build phase. Okay, so that's untouched. We never touch that. And in fact, later on, we might want to come back and rebase our fork and pull in all these changes. And that has an interesting property of never having a Git conflict when you rebase because we never touch the original descriptor. Does that make sense? So there's some interesting power here in this model. So we've dropped this in. We have a customization YAML file. And we're telling it, put everything in this namespace, pull in the original YAML descriptor alongside a new one that I've proposed. This has some persistent volume claims in it that refer out to those disks. A patch, this basically, we'll take a look at this in more detail here in a second through a little easier to see interface. 2 patches, one patch that uses a strategic merge, and the other, and this is a bit of a criticism of this tool, which uses the very confusingly named patches JSON 6902. Very bad product name. We need some PM on this, I think. But the general idea is this is referring to RFC 6902 and the RFC that tells you how you can apply a patch to JSON in very sophisticated ways. And so we need this. We need more sophisticated ways. Actually, let me pop back to the diff to show you why we need this. So I'm showing you a delta between master and demo step 1 branch. Does that make sense? Okay, so this is the same thing on the file system. I'm just showing you a diff view so that it's just showing you what I've added. All right? So that's the customization file that we just looked at. This vol mount patch is the piece that's needed to get a little bit fancier. So instead of a strategic merge of just adding new volumes in, what we want to do is you would think about like reaching down into that original YAML and just snipping off with a pair of scissors all those volumes that were specified and replacing it with a new set of volume specifiers. Okay? We need that because we don't want to do this additively. We want to just replace it. And so it supports a relatively sophisticated ability to provide an op type. We could do replace. And then this looks kind of XPath-like. You're just pathing down into that object graph and saying operate on volumes, and then replace what's there with what's provided below. So again, our goal we're navigating towards is to use these persistent disks. And so this references the PBCs that we've defined. And I've made one other small change. This other patch says, change the original deployment to a strategy type of recreate. And I did this for demo purposes. I wanted the original persistent disks to stay there. I didn't want new pods to be spun up and new disks to be spun up. I wanted to retain those disks and destroy the pods and recreate. Hopefully everybody's with me on this. OK, so over on the file system, customize build. And everything goes to standard out. Let's make that look a little nicer. So we can just look through this and see what's going on here. Here's our new persistent volume claims. Nothing too surprising there. Here's our service definition that exposes the ports, SSH, HTTP. Here's our deployment specifier. You can see that that patch has been applied. There's recreate. That's the recreate patch that was applied into the original deployment. And here we know that our fancy patch, we could call it, worked because it's replaced it with the persistent volume claims. There's no reference to that original host path. Okay? And then we had to do one other thing. There's a new storage class that's defined. This says, this is because we're on GCP. We're saying use the, where is it specified? We're saying use, yeah, here it is. We use this provisioner here. We want to use the GCE persistent disk provisioner, and we want to retain those disks that are created. This is for demo purposes, so we don't want to blow away those disks, but it will just keep them there rather than trying to recreate them. So to kick us off, I actually have this working here. I'm just going to port forward in onto port 3000. And the way we'll know this works is if I hit refresh here, and we see a screen that looks GitHub-like. Oh, there we are. OK, so that worked. Good. So we can sign in, and everything looks good. This checks out. So that worked. That's fantastic. But let's convince ourselves that this really did work. So I'm going to pop back into the Google console, and I'm going to look at storage. I will zoom in here a little bit for you. And you'll see I've got data and root. So those are the persistent volume claims that were specified in our YAML, kicked out to that GCE provisioner, provisioned up, and mounted back into the pods that we deployed. We can take a little bit closer look into the pod itself. So if we click in, we've got single deployment. That deployment, again, has a single pod, drilling into the pod. Some details about the pod, things sort of look good and unsurprising here. Here's our services exporting those same ports. OK? Good. So I think that's good for step one. But remember, what we're navigating towards is this. We want to do more fancy things. So we want to use not SQLite, but we want to use a real database. We want to use Postgres. So let's point it at Cloud SQL. And we want to use a hosted Redis instance as well. So Gitee supports using Redis as a caching layer. And to store our credentials for the database, we want to use KMS and GCE as well. And so we do all those things in the next branch. So let's check that out. Step 2. So I just checked out step 2. Looks very similar. I've got a couple of extra files here that you might notice. Specifically, and probably most importantly for this part of the demo, is app.ini. So Gitee allows you to configure it in very sophisticated ways with this initialization file. So this is nothing to do with Kubernetes, nothing to do with customize. This has everything to do with the application that we are deploying and tailoring to our specific needs. So there's that, and then there's psql.secret. So this is an encrypted binary file that is decrypted at customized build time, and I'll show you how that works here. So again, I'm going to pop out to a diff. So this time we're diffing step 1 and step 2. So this is, again, just to kind of isolate the differences in what the steps are in our demo. Coming back down to customize. So what we're doing here is really mostly configuration in this step. We're using this config map generator that I referenced earlier as we were looking at the various features. And we're saying pull in app.ini off the file system, map it into a config map called app-config. And then we're using something called secret generator, which I have not talked about, but is very, very similar to a config map generator. It lets you basically run a command, take the output of the standard out of that command, and load it into a Kubernetes secret. And so this is calling gcloud KMS decrypt. And you should see that psql.secret. So that's the encrypted binary file sitting in my file system that's checked into this branch. Specify the key ring and the key. Running this will emit a secret, just a few characters that is the password to the database. That gets pulled into a secret called password. And we'll see that in a couple of different places. So that's effectively what's going to happen when we deploy this. This deployment patch specifies a couple things, nothing too fancy here. We're just telling the Gitee app to go out and look for its custom app.ini in that directory. And then we're saying inject PG password into the environment from this secret ref, Postgres password. And so the Postgres library that this system uses happens to look for this PG password. And so it's a convenient way to get credentials into the system without putting them on a file system or doing something other like this. So that just happened to work out easily here. And then we're vol mounting that config map in here. The app.ini, I'm not going to go through this in detail. I want to point out just maybe 2 or 3 things. One is the default theme, arc green. So you noticed before it was white. So if things work in a moment here, I'm going to apply this out to that cluster. I'm going to hit refresh. And the way you're going to know this worked is if it goes into this dark mode. So cross your fingers. And I specify Redis here. This is the address of a hosted Redis instance I've got in GCE in that account. And if we scroll a little further, we see it's not using SQLite. We're saying use Postgres. And that's the Cloud SQL database I've got in my account and the password that it's provisioned up, or the IP rather, for that database. OK, so a Customize build. This looks just like the example I gave. Build, we're going to pipe it straight into kubectl apply. Get pods. Okay, so this is triggering a redeployment so that that pod is terminating. New ones are spinning up. Should say running a second here. This is a dramatic pause. Running, okay. You didn't think that was going to work. I'm going to report forward that, and I'm going to pop over here. And if I hit refresh, this white theme should go to dark, and that will tell us like everything worked. That'll tell us that the theme worked and our database connectivity worked, and there we are in dark mode. Let's sign back in. And this is slightly different because this is now actually pointing out to the database and is using the state from my previous invocations of this. But we can convince ourselves that this is working by looking at the application's configuration itself and zoom in on this a little bit. You can see the application is telling us in its config page for the admins, this is using Postgres. So we know that Postgres piece worked. We know the Redis piece worked as well as telling you that the Redis thing worked. If we hop over to the console, the cloud console, we can see some other interesting things. So before, I believe I showed you these. I don't know if I showed this or not. But these are the PVCs that were provisioned up, the volumes. We can go back and look at the config maps. So this stage of the demo actually went out and created those config maps. Remember, the config maps get unique names. And so what do you notice here? You notice that these config maps are sort of piling up, right? Because every time they change and get deployed, a new one gets created. And so there's a couple ways of addressing this. You could create some sort of garbage collection thing. You could be brave as well and use the kubectl apply -- prune. If you're familiar with -prune, you can give it a label and it will sort of clean things up for you. But I'm letting these stack up more for demo purposes than anything. I'll click into this Postgres secret, and we should be able to see something that says password here. My browser just. So here's password. So hopefully you can see sort of how this secret threaded its way all the way through. It pulled it off the file system, gcloud, KMS decrypt. It pulled it into the YAML descriptor. And then when we deployed it out, it pushed it out, provisioned up this new Kubernetes secret that is then mounted into the environment of this application and used to go out and authenticate against the database. OK, so that all looks good. Looks like we have time. So let's do the third step here. Demo step 3. Again, very similar stuff on the file system. You'll notice Envoy mentioned twice here. So I've got an Envoy patch. And this Envoy patch is the piece that says, add a new container to that pod spec. And envoy.yaml is the configuration for Envoy itself. This is not Kubernetes related. This is not customized related. This is what Envoy needs in order to forward things around. So let's take a look at the deltas. So this compares branch 2 and 3. Coming up to the top here. So Envoy patch, this is the piece that actually injects the container. So the patch says, reach down into this deployment and add via strategic merge this Envoy container. Here's notice this Envoy Alpine. And expose off port 9211. Remember from our diagram what our goal is here. Our goal is to come in from 9211, have Envoy forward us across here, and we get all the benefits of Envoy. What are the benefits? The benefits are this is the building blocks of a service mesh. So to have a service mesh, you're going to need something like this. But even independent of a service mesh, you get some interesting properties out of this. You get very, very rich uniform observability by injecting sidecars like this. So you could emit stats from a configuration like this to your observability systems. Similarly with logs. You get interesting behavior, like you could tap into the rate limiting capabilities or circuit breaking capabilities of Envoy. This has really, really rich potential to implement this sort of thing. So that's that. And then here's the Envoy YAML. This is about as simple as you could possibly get for an Envoy config. Envoy's configurations can be quite complicated. This basically says listen on all IPs, support 9211, and forward those to port 3000 on localhost. And so since these are in the same pod, localhost forwards over to the existing application container. Okay, hopefully that makes sense. There's a reference to the patch and customization YAML. So let's just apply it. So I applied it. I'm watching the pods, terminating, creating. So the way I know this is going to work is if I go back to that browser window and I change the port from 3000 to 9211, and if things work, then we know we're transiting through the sidecar and we're hitting the original application. So down here, I have been port forwarding 3000, so I'm just going to change this to 9211. OK, we're up. My port forward is up. And I can go over here. I can change this to 9211. And the sidecar works. OK, so we know that's working because otherwise we would just get like errors here. So hopefully that gives you a taste for some of the primitives that exist in Kustomize as a tool. Lots of places you can go for additional info. The original GitHub repo is probably the canonical place to start. The declarative app doc is really good. SIG-CLI goes deeply into Kustomize and its future. There are some KEPs on this. On the Kubernetes Slack, there's a Kustomize channel. Jeff, one of the key maintainers, also recorded a talk on this. You can find that on YouTube. And there's interesting integration with other tools as well. There's a company called Replicated doing some cool stuff with this. KubeBuilder automatically kicks out support for Kustomize, and Scaffold as well. So Scaffold is a development a tool for your development workflow, your sort of inner loop. And that actually has support for customized deployments as well. So lots of other places to go. Quickly worth mentioning the road ahead. kubectl, this support for Kustomize. Basically, Kustomize is getting merged into kubectl. You can read this cap here. I was just talking to Ahmed literally before I walked up on the stage, and he was telling me that there are PRs out there right now that will be merged in a few days' time, probably. And this should land in Kubernetes v.next. So that's happening. And then I would encourage you to think about some of the primitives and then interesting workflows and sort of separate those things. So Kustomize is a simple tool. It's a command line tool. But it implements some very interesting primitives that can be composed into very sophisticated workflows. So I'd encourage you to go take a look at it. If you want to find out more, want to talk about it, I'm around the conference all week. So thank you very much. About 3 minutes for questions, if there are any questions. Yeah, go ahead.
Hi. Right now, what I do that there is like, let's say, two school of thoughts. One of them charts, one of them is YAML. And I feel that it's always hard to figure out.
Yeah, so the question is like, there's different schools of thought. There's charts and there's YAML. Which do I use? And my answer is, why not both? Why not both? So Google around for some examples that have been created of taking Helm output and using Kustomize on it. So the challenge you'll have is, if you want to use Kustomize in the way I've just described, you have to go find upstreams that are publishing YAML descriptors. And those are very far and few between. However, what's much more common are charts that will output YAML. So I would encourage you to sort of like take a look at like maybe fusing those two things. Yeah.
Does Kustomize know anything about Kubernetes as far as, say, sequencing namespaces first for creation operation?
It does know about that. Yeah. If you dig into the source code of Kustomize, it has special sorting that will create things in the order necessary. Other questions? Yes.
I think it's cool that you avoid the merge conflicts when you rebase the upstream, but then you kind of move those merge conflicts into hidden conflicts that would happen when the overlays don't match up and change the outcomes.
What's the question?
Would it be better to see the merge conflicts in Git in that case?
So it depends. So the question is like I made the statement that when you rebase your fork, you won't have merge conflicts, which is true. A valid point was made though, like still things might not work. Is that your point? Yeah. So it depends on when you run Kustomize build. Do you run it at deploy time when some end user is clicking on deploy, or do you run it and check the results into Git? So if you run it and check the results into Git, then you could diff the results between invocations of Kustomize build. So that hopefully answers your question. Yeah.
We found it's very helpful to do to check in the compiled output and the actual using our kind of our own similar tool.
Sure.
But I wouldn't be able to do that with the secret generator, I'd imagine, because that's just spitting out the plain text Kubernetes secret. Probably.
Yeah, I didn't show it, but basically the Kubernetes, the secret was there, and it was not encrypted, it was just base64 encoded. So yeah, valid point, secret handling is a larger topic, yeah.
We haven't figured it out either.
Okay,
But you wouldn't be able to run build and then check that if you have the secret generator.
correct. I suspect you'd probably use something like Vault if you're really doing this for reals, yeah. Yep,
Is there any concept of validation? So like a US endpoint, how would you try to validate that?
I'm not sure I followed the question. Is there a validation concept?
Right, so like, how do you know that Ria's endpoint exists if somebody didn't configure the URL?
Which endpoint?
One of the overlays was like connecting to.
Oh, I see. I mean, it will error out if it can't resolve one of the dependencies.
Sometimes they fail silently, right?
Okay, it's possible. Yes.
But there's no real validation of overlays.
No, but I mean, again, it's to be composed in with other tools. So I would encourage you to look at something like KubeVal to validate the actual output, or some like generic YAML validator as well. So, okay, looks like we're out of time. We can find me down here if you want to talk more about it. Thank you very much.